So, welcome to the new video in this series on numerical linear algebra, and this video is about the QR factorization. So, this video we're gonna motivate the definition of the QR factorization and actually give you a procedure to computing this factorization. So, let us start by motivating this. You might have seen the problem of solving for x in this linear equation, and one standard way that you might have learned is to apply the Gaussian elimination to the matrix A and transform it to row echelon form so that you can solve for x easily. Now, let's just imagine for a sec that you have a matrix that is a 100 by 100 matrix, and you want to apply the Gaussian elimination to that. So the number of entries that you will have to zero out is 100 squared minus the number of diagonal entries. You'll be actually doing a lot of computation, and this has a high computational cost. So the goal henceforth is to try to minimize this computational cost by introducing some new algorithms and tricks probably. So one way to reduce the computational cost, though it doesn't reduce by much, and we're gonna learn much more effective ways in the future, is to use the QR factorization. Well, this is not the only useful property or application of the QR factorization, but this is one way to motivate it. So suppose for a sec that instead of a full matrix A, you had a matrix that is upper triangular, meaning it has zeros below the diagonal. So now if you want to apply the Gaussian elimination again to that, you will only have to zero out the entries that are above the diagonal, which means now instead of you having to zero out this amount, you will have to zero out half that amount or half that number of entries. So the idea of the QR factorization is that if we can magically transform a problem of this form to solving a problem where we have, instead of A, an upper triangular matrix, like we're going to be reducing the cost to the half. So and the assertion or my claim is that you can, and the way so you can turn this problem into a problem of this form, probably B prime, where R is an upper triangular matrix. Now, to do that, let us start by, or to explain how to do that, let us start by defining the QR factorization of a matrix. Now, given any matrix, and for simplicity now assume that A is a square real matrix, though this definition or theorem applies for a general matrix. The assertion is that you can take any matrix and write it as a product of two matrices, one of which is upper triangular and the other is unitary. So I'm gonna define a unitary matrix to you, but I want to say that you could transform a matrix A to an upper triangular matrix R, but you're paying a price of multiplying by this unitary matrix. And let us recall that a unitary matrix is just a matrix whose inverse is its transpose. Okay, so let us see how to do that. Okay, well, before I explain to you the procedure of calculating the QR factorization, let me just tell you the usefulness of that. Again, the usefulness of that is that you start with a problem of the form ax equals to b, and you replace a by the QR factorization of it, and then what you're gonna do is that you're gonna multiply both sides by the inverse of q, which is the transpose in this case, and you'll be getting an equation of this form. and this is just a vector. This is a vector b prime, and you'll be instead of solving ax equals to b, you will now have to solve rx equals to b prime, where r is just an upper triangular matrix. So you will only have to zero out the diagonal, the entries above the diagonal, which is half the number that you had to zero out in the beginning. So let me explain to you how to do that, or what's the procedure of finding the QR factorization. So if I tell you how to find the QR factorization of the matrix, you can apply this procedure and you'll be reducing the problem to the half. Okay, so let me start off by explaining to you how to get the QR factorization of a matrix. So let's say you're starting with a matrix A, okay? And let's write it as A1 through AM. By the AIs, I mean the column. So this is the second column, this is the nth column, okay? And the hope is that that we can transform A to some unitary matrix. Let's write it as Q1 through Qm. Now, to do that, of course, we need some machinery, we need some tool to do that. But let us see what is it that we require from the Qi to satisfy. Well, it's quite an easy and standard exercise to show that the unitary matrix has columns that form an orthonormal set. And what is that? It's just a set where every vector is orthogonal to one another, in the sense that if you take the dot product of any two of them, you get 0 unless you're dotting the vector with itself, in which case you get only 1. Okay, and this every vector is normalized. Now let's see if there's some tool to do that. Okay, so the idea again, let's recall it one more time. We're gonna take we're gonna start with A that has an arbitrary set of columns, and the goal is to transform this into a matrix Q with columns that form an orthonormal set. Okay, so let's say we could transform these columns to that matrix. Will be actually done. We've actually found the QR factorization, because recall the goal is to define A to be QR, and then we can just define R to be Q inverse times A, in this case Q transpose times A. From this equation we can get R immediately. So it boils down to defining what the Q is, or finding a way to transform the matrix A into a unitary matrix Q by transforming the columns to an orthonormal set. So this is a very famous procedure that allows you to take a set of vectors and gives you an orthonormal set of vectors, and this is called the Gram Schmidt procedure. And it goes as follows. So what you're gonna do is that you're gonna proceed by induction to orthonormalize the set. So you start with the first vector, A1, and I mean, there's nothing to orthonormalize with. So what we're gonna do is that we're gonna just normalize the vector A1, and we're gonna define this to be Q1. Now there is an issue if A1 is 0, is a 0 column, then we're gonna just take Q1 to be any normalized vector. In this case, we're gonna take, for simplicity, we're gonna take E1. Okay. So now we've constructed a Q1, and the next task is to construct Q2. How do we do that? Well, the procedure tells you to do the following. And this is a standard trick that gonna show up a lot So here's the idea. What is it that we require from Q2 to satisfy? Well, we require Q2 to be orthogonal to Q1, and we want Q2 to be a normalized vector. So how can we do that? So the idea is that we start by defining a vector v2. And this vector is going to be the new vector, that is in this case a2, minus the projection of this vector. So we're going to subtract the projection of the vector a2 onto the space spanned by q1. And the claim is that we're gonna get an orthogonal vector to q1. So before we actually prove this, or before we actually check this, let me just tell you that there is one more thing to do. You see, we can't just take a v2 because there's another requirement, which is that we want this to have a norm 1. So what we're gonna do is that we're gonna normalize the vector that we know is orthogonal to q1. Okay, so this is our definition of q2. And now let me motivate to you why this definition of v2 is the right definition to take. Well, let's say okay, so in this case you have a space spanned by q1. Okay, this is the vector q1, and you have a space spanned by it, and you want to take the vector a2 and you want to get a vector that is orthogonal to q1. So how do you do that? So one way of doing that is by projecting a2 to the space, and you get this vector, and the procedure is telling you that to get a vector that is orthogonal to q1, all you have to do is that take the a2 vector that you have and subtract from it its projection. So in this case it's this bit, this vector. So if you subtract it, it's going to be the reverse vector, and it's clear now geometrically that you'll get a vector that is orthogonal to the space spanned by q1. So this is just a geometric rough idea of what's happening, and let us check this algebraically. So let us check that it is true, it is a case that v2 is orthogonal to q1. So to check that, all we need to show is that the dot product of q1 and v2 is actually 0. So let us dot product q1, or let us multiply q1 transpose times v2, and if we do that, this is the equation that we'll be multiplying by. It's this one. So what we're gonna do is that we're gonna just distribute, and this thing over here is just a scalar because it's the dot product of a2 and the q1, so it's just a scalar. So we can get the q1 to next to the q1 transpose next to the q1 here. And well, we started by defining q1 to be a normalized vector, so q1 transpose q1 will just be 1. Okay, because recall, what is if you take a vector v and dot product it with itself, you just get the norm of v squared. In this case, it's going to be since q1 is of norm 1, it's just going to be 1 squared, which is 1. Okay, and what we are going to get is that we're going to get the dot product of q1 by a2 and the dot product of a2 by q1, which is just the same thing, and this is clearly 0. So it is indeed true that v2 is orthogonal to q1. So what's the next step? What do we do? Well, let's do the induction step. Okay, so let's suppose that we have formed I minus 1 vectors. Okay, and we want to form the ith vector. How can we do that? Well, the idea is that we're going to take these vectors, we're going to take the span of these, let's call it a set S. And what we're gonna do is that we're gonna do the same thing that we did for the case when S is equals to just Q1. So we're gonna define a vector Vi to be the new vector, which is AI in this case, and we're gonna subtract the projection of this vector AI let me just write it more clearly. This vector AI, we're gonna subtract the projection of this vector AI onto the set S. So just as we did for the previous case. And it is clear that us doing that, we will get a vector in this span, meaning we're gonna get a linear combination of the QJs, right? And what kind of linear combination will give us the desired result? It is the linear combination where we take the scalars, or we take the scalars and the linear combination to be just the dot product of AJ with QJ. Okay, and just as before, we can check by dotting with QI both sides that this vector Vi will be orthogonal to the vector Vi. So in this case, there is one more thing left to be done, which is that we want to normalize this vector that we've gotten. So we're going to define Qi to be just the normalization of this vector. And this is actually the Gram Schmidt procedure. So let us recap what we've done. We've started with a matrix A of arbitrary columns in it, and we've transformed this using the Gram Schmidt orthogonalization to a set that is an orthonormal set, right? And it is again easy to check that if you take Q to be like the columns formed by this set, it is easy to see that Q will in fact be a unitary matrix. So now that we formed this unitary matrix, we can get R easily by just defining it to be Q transpose times A, and we can add the R in a different way by following the constants we were taking linear combinations with in the Gram Schmidt procedure. So thank you